take a limit, what we're really trying to find is not necessarily what is the value of a function, but what is the value of the function approaching. So we'll get into this a little bit more next time. But if I want to say, what's the limit as x approaches 5, I don't really care what the function equals at 5. I want to know what is it approaching as we get closer and closer to 5. We'll do more of those kinds of limits next time, but today I want to talk about limits at infinity. In other words, what is the value of the function approaching as x gets closer and closer to infinity or negative infinity? As the graph goes to the right or to the left, what is the value of the function approaching? And we have a good definition for these infinite limits, or not infinite limits, but limits at infinity. And that is horizontal asymptote, which is something that you probably studied last year in pre-calculus. Okay, a horizontal asymptote defines the end behavior of a graph. It tells you exactly what the value of the function is approaching. Okay, so let's take a look at this graph right here. Now, I know the grid didn't really print very well, and you can hardly see it on here, but let's just use our best judgment. What does it appear that the horizontal asymptotes are? Yeah, it kind of looks like we have a horizontal asymptote right here at 4, right? And 1 at -1. Now, one thing I do want to make clear is that, back in the day, at some point, you may have been told that, sort of a casual definition of an asymptote is that, oh, this is a line that the graph cannot cross. That's not true, actually. A graph can cross an asymptote. An asymptote simply defines the long-term behavior of a graph. So you could potentially have a graph that has an asymptote, let's say here, and the graph does something like this, where it crosses it many, many times, but as x goes closer to infinity, the difference between the value and the function, the asymptote, goes to 0. It's getting closer and closer to that asymptote. Okay, it's approaching that value. Now, if we look at these two asymptotes, yeah, we can see we have one at y equals 4 and one at y equals -1. And so the way that we're going to describe these asymptotes using limit notation is to say the limit of the function, so the limit of f of x as x goes to the left, which is negative infinity, is 4. So the value of the function as x goes to the left is 4. The value of the function as x goes to the right, and we can write that as the limit of f of x as x approaches infinity, is what? -1. So really, like, your key takeaway from today should be that limits at infinity describe the horizontal asymptotes of the graph. They're the same thing, essentially. That's what a horizontal asymptote is. It describes the limit at infinity. So we kind of already did this, but okay, write the equations for the horizontal asymptotes. We did that. We already determined those limits. We already did all that. So here are the answers. Here's the equations. Here, this is like your answers to A, and here's your answers to part B. Any questions? Y'all remember doing horizontal asymptotes last year? Now, usually, like when you're first introduced to horizontal asymptotes, you are introduced to them in terms of rational functions. You talk about rational functions, you graph. Teachers teach that all kinds of different ways, but you basically learn how to find the horizontal and vertical asymptotes and x-intercepts and y-intercepts and holes, and most importantly, end behavior. The end behavior component is really what we're focusing on today. Okay. So how do we do this algebraically? Does anyone remember how to find horizontal asymptotes of a rational function from last year. Yeah, what do you remember from that? Or you just give me anything to work with.
Is it the ratio of the leading coefficients?
It may be the ratio of the leading coefficients. That could happen, and that happens in a very specific case. Okay.
The powers are equal to each other.
Right. So if the degrees, and we'll go into why that is here in a second, because I don't want you to memorize all these rules. Powers are the same, it does this. Powers are bigger on top, it does that. Don't worry about any of those rules. I'm going to show you a better way to think about it. But yeah, you're right. When the degrees of the numerator and the denominator are the same, the horizontal asymptote is the ratio of the leading coefficients, which in this case would be what for number 1? 1, right? Or 1/2, yeah. But I want to show you a different way to approach this. And this strategy is going to be helpful for more complicated functions. The function 1 over x. Let's consider this. Okay, so we'll say f of x is 1 over x. So the numerator is constant. The denominator is variable. What happens as x goes to infinity in a function like this? So like as x gets bigger and bigger, if you consider these fractions, 1/2, 1/3, 1/4, 1/5, you just keep going. What is the value of that sequence getting closer to? 0, right? Makes sense. You divide by a bigger and bigger number, you're going to have smaller and smaller. You have one pizza, cut it up into more pieces, the less pizza you get, right? And if you cut it up into infinitely many pieces, you get no pizza. So this is getting closer and closer to 0. So what we could say is that the limit as x goes to infinity of 1 over x is 0. Yeah? The graph looks something like this. So as x goes to infinity, it goes to 0. All right. So let's consider this a little bit differently. Did anyone have a teacher that taught like Bob-Yo, Botno, Eats DC, or anything like that? Does that sound familiar? Okay, yeah. You don't need to worry about any of that. Okay, I'm going to show you a different way to approach this because I'm not a fan of like memorizing rules. I'd rather you understand like why those rules even are what they are. Yeah. So let's approach this algebraically. For number 1, what I want us to do is to factor an x squared out of both the numerator and the denominator, as though it was like a GCF. Okay, the greatest common factor. It's not the greatest common factor, but we're going to factor it as though it was. So let's rewrite this as like, let me make it a little smaller here. Let's see. So f of x. So if I factor out an x squared out of that top, what goes in the parentheses here? Like what's x squared divided by x squared? 1. Okay, good. And then 3x divided by x squared. So do a little quick math onto the side here. What would that reduce to? Yeah, 3 over x. Okay, so plus 3 over x. And then minus 28 over x squared. Right? Does that seem reasonable? Okay, very good. And let's do the same thing with the denominator. So I'm going to factor out an x squared. And so same kind of deal here. I'm going to get 2 minus 14 over x squared. Now this looks way more complicated, right? This is not something you would do if you were like simplifying it. But what we're trying to do is understand what the end behavior is. What's happening as x gets closer to infinity? Now I factored out the x squareds. Assuming x isn't 0, and it won't be if we're going to infinity. What's x squared divided by x squared? 1, right? So these will just reduce to 1. And so we've got f of x equals 1 plus 3 over x minus 28 over x squared all over 2 minus 14 over x squared. Okay, so we've got a bunch of stuff happening here. Let's think about what's happening as x goes to infinity now. The end behavior of the graph as we go further and further to the right. So x is some arbitrarily large number. 3 over x, what is that getting closer to as x increases? Yeah, it's just 0, right? As x gets bigger and bigger, this whole thing goes to 0. As x gets bigger and bigger, what's happening to this little fraction? It's going to 0, right? And maybe you kind of see what's happening here. Is that all of these fractions that have a constant on the numerator and a variable in the denominator are all going to go to 0. So if I want to say so if this thing's going to 0, and this one's going to 0, and this one's going to 0, as x goes to infinity, okay, then what is this whole thing getting closer and closer to? 1 over 2, yeah. So f of x gets closer to 1 over 2. So the equation is just 1/2, which you knew from the beginning, yeah, or some of you, if you remembered the rule, yeah, but I don't want you to think about rules. I want you to think algebraically and, what's happening. So this is another way we can find horizontal asymptotes. This way you don't have to remember the whole Bobbio botnote. Now, if you remember that and you want to take that shortcut, that's fine. The key thing here is that if the degrees are the same, then the horizontal asymptote is just the ratio of the leading coefficients. But this is why. It's not just because. Yeah? Okay. Now, thinking back to pre-calculus, maybe even algebra 2, what was the horizontal asymptote when the denominator had a larger degree? Remember that? Yeah, 0, right? Let's find out why. Yeah, why would that be? Well, let's take the exact same approach we did here. We are going to factor out whatever the largest degree term is. So in this case, the largest degree term is this x to the 5th, right? So if I factor out an x to the 5th on the numerator and the denominator, x squared divided by x to the 5th would be 1 over x cubed, which as x goes to infinity, that fraction is going to go to 0, right? Plus 3 over x squared. Again, that's going to go to 0. Wait a minute. Did I do that backwards? And then 3. No, that's right. Yep. Yeah, x squared. That's going to go to 0 as well. Do the same thing on the bottom. It's going to be 1 x to the 5th divided by x to the 5th. X squared divided by x to the 5th. I'm sorry, 2x would be 2 over x to the 4th. And then 1 divided by x to the 5th. Just 1 over x to the 5th, yeah? So if I want to send x to infinity, first of all, before I do that, we can cancel out these x to the 5th, so we don't need those anymore. Those will reduce to 1. Right? That's just 1 right there. And so now let's send all the x's to infinity. Plug in some huge 100 million bazillion into x. So what is the 1 over x cubed going to get closer to? 0, yeah? So this is just going to get closer to 0. This is going to get closer to 0. All of these fractions are going to get closer to 0. And so this whole thing is just going to get closer to 0 over 1, which is 0. And that will happen every time the degree on bottom is bigger. All right, so yeah, the horizontal asymptote here would just be y equals 0. Any questions so far? Now, what happens if the degree on top is bigger? You guys remember what happens in that case?
The numerator's degree would be
So what's the horizontal asymptote? Or did 1? Like, it won't be constant. You know, I'll say that much at least. Yeah. Well, back in like algebra 2, you probably just said there is no horizontal asymptote, and it's an oblique asymptote. And depending on your class, you may have even found that oblique asymptote. We'll get into that later, but the key point here is there just isn't one. There's no horizontal asymptote if the degree on top is bigger. And here's why. Let's just go through the algebra the same way. If we divide out an x squared here, and we send x to infinity, make x really, really big, each of those fractions are going to go to 0. So we get the x squareds to reduce to 1. All the fractions go to 0. And so we're left with 1 over 0. So what's 1 divided by 0? It's undefined, right? No, there's no answer, which is why there's no horizontal asymptote. Okay? So there's no horizontal asymptote. Now we'll get to a point here pretty quickly where even though there's not a horizontal asymptote, we can still give a little bit more information and say what's happening with the graph. This is what happens is like for instance, this quadratic over here has no horizontal asymptote. Right? The graph is not, the value of the function is not approaching a certain number. It's just going up to infinity. And so we do want to be able to say, hey, is it going to infinity or negative infinity? It will be one of those two things. We don't need to worry about that quite yet. So these are the 3 cases. Now, if you know your whole Bobbio, Botno thing, you can go through this a lot quicker. But I think once you get the hang of just looking at it, and after you practice a few of these, it'll become a little bit more natural. Yeah. So, like on this one, let's divide out like a 3x cubed. Or let's just do x cubed. Let's keep it simple. So we get 3 plus 5 over x squared minus 10 over x cubed over x cubed is what we're factoring out here. So we get 2 over x plus 1 over x squared minus 14 over x cubed. Just factoring out that x cubed. What's the horizontal asymptote going to be for this one? I was assuming a little bit. It's going to be undefined, right? And you can see that in the math here, right? These cancel out. These all go to 0. And so we get 3 divided by 0, which is undefined. Yeah, so no horizontal asymptote. So you don't need to memorize like a mnemonic device that's like 12 letters long. Bobbio, Botno, you don't need any of that. Just divide out that leading term and see what zeroes out as x goes to infinity. All right, I don't know. Is this making sense? Are you guys following along here? I don't know if we need to do any more examples here. So let's try to do it quicker. Okay, so let's just look at it. Do the factoring in your head. Okay, and you don't even need to like do all the factoring. Just think about like what's going to zero out. So like here, what term am I going to factor from the numerator to the denominator? X cubed, right? So if I factor out an x cubed, the only thing that's not going to turn into a fraction is going to be this thing, right? It's just going to be a 1 here. This is all going to zero out. And you'll just be left with 0 over 1, which is 0, right? Bigger on bottom, y equals 0. So the only terms you really need to concern yourself with are those largest degree terms. That's really what's going to determine the end behavior. I remember don't know why I remember this, but when I took calculus, I remember my teacher calling all that other stuff spit in the ocean. Okay, yeah, it's like the ocean has a certain volume. Yeah, if you're out on a boat, you spit in the ocean. The volume of the ocean, does it change? Like technically yes, but practically no. Right? Like it's still basically the same amount of volume, the same amount of water that's in there. Right? And so like all this other stuff just doesn't matter. It's too small to really make a difference when x gets really big. Oh yeah, let's keep that. All right, let's do this last one over here. 6. Okay, you're looking for that largest degree term, which is going to sort of set the stage here. It's x to the 4th. Right, it's on top. So if I divide all that stuff out, what's the horizontal asymptote going to be here? Yeah, none. Right. Okay, I think that's enough of that. We'll do some more practice, but that's the basic idea. So if the degree is bigger on top, there's going to be no horizontal asymptote. If the degree is bigger on bottom, it'll go to 0 each time because you'll end up with a 0 over something. And then if they're the same, that's where you get that ratio of the leading coefficients, because both the numerator and denominator will have that extra factor that doesn't go to 0, that constant. All right, so we got three rational functions here. I'm going to take a minute and determine which of these, if any, have a horizontal asymptote. You don't even need to tell me what it is, but let's just go through them. Does one have a horizontal asymptote? Yeah, what is it? I guess you could tell me probably pretty quickly. Yeah, this one's just going to be y equals 1. All right, take a moment to look at number 2. It's going to be 0. And what about number 3? It's undefined. So there's none. All right. So it's really just 1 and 2. Now let's throw in some square roots. Okay. This is where it looks a little bit more complicated. Now, the notation here says limit as x approaches infinity, but we're really kind of answering the same thing. What's the horizontal asymptote? There's a little bit of an issue here, though. We can end up with a graph like this. And we'll get into like what actually happens and when this happens. But notice like this graph has 2 horizontal asymptotes, right? One that's y equals 4 and one that's y equals -1. They're not the same. So if I were to say, what's the limit as x goes to infinity, you would say -1. If I say, what's the limit as x goes to -infinity, you'd say 4. So just because there's a horizontal asymptote doesn't mean necessarily that the function approaches that on both sides. For a simple rational function, yes, that will be true. Right? If it's a polynomial divided by a polynomial, that will happen. But if it's not a polynomial, sometimes you can get more than one horizontal asymptote like this, where basically you have different behavior on different sides of the graph. And that's going to happen here. All right. So here we're going to have to be a little trickier about what we do. Here on the numerator, underneath the square root, let's factor out a 9x to the 6th. Okay, 9x to the 6th. So let's see what happens when we do that. So we'll factor out 9x to the 6th. I'll just include that square root on here. Times, 1 minus 3 over 9 would reduce. So would that be 1 over 3x to the 5th? Is that right? You may need to just, Here, let me write no. That's kind of hard to see, isn't it? Let's change colors. Over. And here, well, let's just leave this as it is for now. I'm not going to mess with that denominator quite yet. Okay, now when you take the square root of a product like this, like if you have the square root of, let's just say, a times b, this is something you did probably starting back in geometry. When you simplify square roots, one property that you should be aware of is that you can split up a product of a that's underneath the square root. In other words, the square root of a times b is the same thing as the square root of a times the square root of b. Yep, not 6. That should be b. All right, so we can split up that numerator and rewrite this as the square root of 9x to the 6th times the square root of 1 minus 1 over 3x to the 5th. Yeah. All right. Now, what is the square root of 9x to the 6th? I want to just simplify this thing right here. What is that? Yeah, 3x to the 3rd. Yeah, exactly. Okay, so this will equal the limit as x goes to infinity of 3x cubed times all this stuff kind of running out of room here. Should give you more room to write this one. Okay, so now we want that 3x cubed. We want to get rid of that 3x cubed, kind of like on all these other ones, how we reduced that first thing to 1. But now notice we've got an x cubed on both the numerator and the denominator, so that's going to reduce really nicely. So let's factor out that, that x cubed. So, do I have room? Oh, yeah, okay. So the limit, as x approaches infinity, of 3x cubed times root 1 minus 1 over 3x to the 5th over, you know what, let's take out the 4x cubed. I think it might make it easier if we do it that way. So this would be 3 over 4x squared minus 5 over 4x cubed. Yeah. All right. So now let's start. This is bad math here, but let's start plugging in infinity. Can't really do that, but let's think about if x gets really, really big, what happens to a lot of these terms? Yeah, a lot of them just going to be 0, right? So you plug in plug in infinity, or you send x to infinity, and each of these little fractions here, like this one and this one and this one, what are all these going to turn into? 0. Yeah. And also, we've got a factor of x cubed on the top and the bottom. So we can reduce those x cubes to 1. So now this is going to simplify really nicely and give us 3 times the square root of 1 over 4 times 1, which is just 3 over 4. But we're missing something here. The square root of x squared. That doesn't just equal x. That could equal both x but it could also equal negative x. It's really going to be plus or minus x. Yeah. So let's take it back a couple steps here. Let's see, when did that actually occur? It's this step right here. There should really be a plus minus on this. Yeah, and that's going to carry all the way through here. So we got to be a little careful about that. There are going to be two horizontal asymptotes, but this function is not going to approach two different numbers as x goes to the right. Instead, it'll one of them it'll go to positive 3/4, and on the other side, going to the left, it'll go to one of the other ones. We need to determine, well, which one is it? Is it positive 3/4 or negative 3/4? We are going to have two horizontal asymptotes. But let's just imagine we plug in some large number, some large positive number into the original function. And think about the signs. So let's say you plug in like 100 million, okay? Is the numerator going to be positive or negative? Positive. Is the denominator going to be positive or negative?
Positive.
Also positive, yeah? Really, you're just looking at those leading terms, right? If this was a negative, if this is like negative 4, then it would be negative. Now, if I plug in like a negative number, like if I plug in negative 100 million billion, then we're going to end up with a negative number, right? This cube is going to be negative. So, to the right, we're going to go to positive 3/4. But if I were to ask, like, what's the limit as x goes to negative infinity, you would go towards negative 3/4. Just want to make that little distinction. I didn't want to like fly by that, even though we do end up just getting 3/4 anyway. But you can see if I flip the question on and say, oh, what's happening as x goes to negative infinity, you get a different answer. Any questions so far? Now let's do another one. Oh, well, yeah, we kind of already answered this one, right? Yeah, so where's this one going to go? Yeah, negative 3/4. So yeah, we're kind of kill two birds with one stone there. And so the horizontal asymptotes of this function are going to be y equals 3/4, but also y equals negative 3/4. Any questions so far? Okay. All right, let's take a look at this guy. Okay, so how are we doing? Are we doing okay? Oh yeah, we're doing really good. Okay, so we've got this function. We want to find the horizontal asymptotes. I want to give you like 2 minutes to see if you could do this one on your own. Then we'll go over and see if you got the right answer. But just kind of a little gut check time here. See if you can figure out. I want you to find. I'll give you a hint. There's going to be 2 of them. Okay, 2 horizontal asymptotes. It'll be very similar to the last problem. But let's see if you can figure out what they are. I want you to like start thinking about patterns and like, okay, well, do I really need to go through all that algebra to get there?
Yeah, so what I did was factor out, so like, it's like, if, forget the square root for a minute, but if it was just like 4x to the 4 plus 1, I'd factor out the 4x to the 4. So it'd be 1 over 4x to the 4 plus 1. So like, this is turning into that, and that's turning into that. Yeah. Yeah, that one, it's just kind of weird the way it turns out. So it looks like it's just flipping, but does that make sense?
What do y'all think? What are we getting here for our horizontal asymptotes here? You want to get an answer? Yeah, just say it. Yeah, 2 over 7. So that's one of them. What's the other one? Negative 2 over 7. Yeah. So what I want you to kind of see, like these square root ones look way scarier than they are. Here's what you want to be doing here is just look for the largest degree term that you can take the square root of, and typically on the AP test they'll be set up nice, so it won't be like square root of like x cubed or something like that where it gets a little messy. Yeah, you just take the square root of that, right? The 2x squared, and then it just turns into they're the same degree, so you just find the ratio of leading coefficients. So you're really only caring about the largest degree terms in there. So our I have my pen here. Oh, there it is. So yeah, y equals, so as x goes to infinity, this is just 1, but 0 plus 1 is just 1 times, so that's just going to be 1. Let's do a different color here. So this is 0, this is 0, and then these cancel out, and so we just get plus or minus 2/7. Feel free to like throw that into Desmos or graphing calculator. If you're curious to see like what that looks like, maybe we can do that if we have time at the end. Any questions about these square root ones? They're very similar. Like you kind of approach them the same way. You just have to know to split up. Like once you factor out that largest one, like you would do anyway, to take the square root of that, and normally they'll be set up so like the cancellation happens pretty nicely. Yeah. Yeah, good. Any other questions? I'm trying to take this pretty slow because I know the algebra is pretty heavy though. And here's the thing that you might find, like the hardest part of this course is going to be the algebra. It's not going to be the calculus. The calculus concepts are going to be the easy part of this course. It's the algebra that you're going to have to practice. Okay, so what happens when you have an oblique asymptote? Like in those situations where we have no horizontal asymptote, like we saw a couple of those up here, right? Like both of these had no horizontal asymptote, but we still want to be able to answer the question like what's happening as x goes to infinity. So either one of two things could happen. Either the function's going to go up to infinity, or it's going to go down to negative infinity. So you want to be able to kind of tell like which one is it going to be. So to find that oblique asymptote, in other words, to find the end behavior, or the function that defines the end behavior, what you need to do is, and you won't have to do this very much, but I just want to kind of briefly go over how you get that, just as a little reminder from Algebra 2, I think, is you're going to divide the numerator by the denominator and disregard the remainder. And you can, if your denominator is linear, you can use synthetic division. Otherwise, you'd have to use long division. But either way, you would just ignore the remainder, and whatever the quotient is, that function is going to define the end behavior. So if your quotient is a polynomial, which would really be the only thing, that's the only thing that's going to come up, where I'm going to actually ask you to do this, is for a polynomial function, the end behavior is determined by the leading term. So you may recall this from an earlier class. But let's say we have something like 3x to the 7th plus 2x cubed plus 1. And I want to know what's the end behavior of this polynomial. So you look at the leading term, and there's two parts to this. You want to look at both the leading coefficients and the degree. Okay, for the leading coefficient, all you care about is if it's positive or negative. Okay? Positive or negative. And for the degree, all you care about is if it's odd or even. All right, I'll make a nice little chart for you to kind of help you remember what's going to happen. So we look at that leading term. So let's start with the leading coefficient. Is either going to be positive or negative. And then the degree, or the exponent, is either going to be even or odd. So if you have a polynomial that has a positive leading coefficient and an even degree, like say x squared is kind of the simplest example of that, the end behavior as x goes to negative infinity and as x goes to positive infinity is going up in both directions, right? So it's going to positive infinity both to the left and to the right. So just to simplify that, I like to just use arrows. Up to the left, up to the right. If that polynomial has a negative leading coefficient, like say negative x squared, that just flips it, right? And so the end behavior is going to go down to negative infinity, both as x goes to positive and negative infinity. If that degree is odd, and the leading coefficient is positive, so think like something like y equals x cubed would be a simple example of that. Yeah. You can see as x goes to the left, y goes down, and as x goes to the right, y goes up. And then if that leading coefficient is negative, it just reverses that behavior. So go up to the left, down to the right. So that, in other words, if I ask you what's the limit of this rational function as x goes to infinity, and you find out, oh, there's no horizontal asymptote, then you have to do the division and figure out, okay, well, yeah, there's no horizontal asymptote, but is it going to positive infinity or negative infinity? And then make that decision. Now we talked a little bit about a couple of functions that we saw that have more than one horizontal asymptote and how to determine which one it's going to. But I might throw out some exponential functions at you too. So exponential functions are kind of interesting in that they don't have two horizontal asymptotes, they just have one. But the limit is only defined going one way, not the other way. And what I mean by that is, if we just sketch the graph of an exponential function, it looks something like this, right? And the horizontal asymptote is y equals 0. Right? It's approaching 0 as you go to the left. But what's happening as you go to the right? As x increases, this thing just goes to infinity. Right? Now if I have e to the negative x, same thing basically, it just flips it. Still going to have the same horizontal asymptote, but that horizontal asymptote is only going to define the end behavior on one side of the function. In this case, the right-hand side. It's like an exponential decay kind of graph. So if I ask you, what's the limit as x approaches negative infinity for e to the x, what would the answer there be? What's the limit of e to the x, that's this one, as x goes to the left? 0. Yeah, and what about if we're going to the right? Positive infinity. You got it. Yeah, and for e to the negative x, that's just reversed. So I'm going to throw a couple of these at you too. All right, we're getting pretty close to the end here. Now, I'm going to give you some weird ones that look like this, where they kind of look like they're irrational functions, but the numerator and the denominator are not polynomial. We can't do the whole factoring trick, right? But instead of doing that, what I want you to think about is how fast are these functions growing? Because that's really going to determine the end behavior. We have, like the polynomial functions we've already dealt with, we kind of know what grows the fastest, right? The larger the degree, the faster it grows. That's why we only sort of focus in on that largest degree term. So if you have something like x to the 10th, that's going to grow faster than something like x squared, which is going to grow faster than something like x, right? So you look at that largest term, I'm saying largest, and what I really mean is it grows the fastest. And everything else is just your spit in the ocean. It just kind of goes to zero. It becomes irrelevant. Yeah. So what's interesting, and this is like, not, I don't think super obvious, especially at first, but every single exponential function that has a base that's greater than 1, we'll just throw that little caveat out there, will grow faster than every exponential function in the long term. Maybe not in the short term, but in the long term. Okay, so even if you have something like x to the 99th power, which you would think grows really fast, and it does, in the long term, something as simple as like 2 to the x, I mean, like maybe make this, will grow faster eventually. I do not think that's obvious. In fact, I think that's almost counterintuitive. Okay. But when you're thinking about like what's bigger on top versus bigger on bottom, if there's an exponential function, it will always grow faster than any polynomial function in the long term. Mm-hmm. Now, as far as the exponential goes, the bigger the base, the faster it grows. So you might have something like, e to the x, which e is like, roughly, it's like a little less than 3. It's like about 2.7-ish. But just so you know, that is bigger than 2. And it's smaller than 3. And you can have like 10 to the x. So if you're trying to determine like what's growing the fastest, what is going to have the biggest impact on the long behavior, it's those exponential functions. Logarithmic functions grow the slowest. And the order there is still based on the base, but it's actually the reverse order because the logarithms are the inverse of exponential functions. So if you have something like log base 2, that's going to grow faster than something like natural log, which has a base of e, which grows faster than, like, say, log 10. All right, so as you kind of get the hang of like figuring out these asymptotes and these limits at infinity, there's really shouldn't be like any work to show almost. Like you should be able to look at the fraction, determine what's growing the fastest, and then come up with the horizontal asymptote just from that. So we'll do a couple together, and then I'll get you starting to work on your own. Okay. So let's look at this one. What's growing faster, the numerator or the denominator? Denominator, right? No, numerator. Exponential grows faster than polynomial. Numerator will grow faster, for sure. So what's the horizontal asymptote when the numerator is growing faster than the denominator? Like, for example, if you had something like x cubed over x squared, it would be undefined. There'd be no horizontal asymptote, right? So when there's no horizontal asymptote, so say no horizontal asymptote, that means we need to determine if it's going to infinity or negative infinity. So just imagine you plug in some arbitrarily large positive number into there because we're going to positive infinity. Is that going to be positive or negative? Just plug in like 1,000. It'll be positive, right? So this is just going to be positive infinity. All right, for the next one. What grows faster, the numerator or the denominator? Denominator grows faster. Right? Log is very slow growth. Yeah. So what do we say is the horizontal asymptote or the long-term behavior when the denominator is growing faster? Like, for instance, like 1 over x. 0. Yeah, it's just 0. So you see how there's not really any work to show here? You just identify what's growing the fastest, and then it's either going to be plus or minus infinity, 0, or the ratio of the leading coefficients. All right, so here, we're really just looking at those I say largest, but I mean like the fastest growing terms, which are these e to the x's, right? So this is a case where you have the same rate of growth on both sides. And so to determine that horizontal asymptote, you just divide the leading coefficients, just like you do with a rational function. So what is this getting closer to? Negative 3. You got it. Yep, 6 divided by negative 2. Oh, here's a tough one. This one's a little weird. So this is actually going to use something. We're getting a little ahead of ourselves here. This is going to use a limit property that we'll focus on later. I just want to give you a little preview. But when you have a sum like this, you can split up the limits and say that this is the same thing as saying the limit as x approaches infinity of 1 plus the limit as x approaches infinity of 2 over 2 plus x squared. We will definitely come back to, but I just want to give you a little taste of what's to come. Let's ignore that one on the left for a minute and just do the one on the right. What is this limit going to equal? And maybe I should ask first, what's growing faster, the numerator or denominator? Denominator. So what's the limit as x goes to infinity when the denominator grows faster? 0. So this is just going to be 0. Now this function over to the left is just 1. It's a constant. It doesn't change. It's always 1. It's a horizontal line. So as x goes to infinity, what is this thing going closer to? 1, yeah. So you have 1 plus 0, which is 1. What's growing faster, the numerator or denominator in this last one? Denominator. You got this x squared. Now be careful here. Remember, the exponential functions will have different behavior to the left and to the right, like those square root ones. Okay, so you got to be careful and you ask yourself, okay, well, as x goes to negative infinity, what is this thing getting closer to? Like if it's just e to the x, imagine the graph. So as x goes to infinity, y is going to infinity. But as x goes to negative infinity, what is that getting closer to? 0. So in fact, as x goes to negative infinity, this guy, this is kind of a trick question here, is actually going to 0. Just that term. And it is no longer the fastest growing term because it's going to 0. And so the actual fastest growing term is going to be this x squared. So when it's bigger on top, no horizontal asymptote. Yeah. So that means we got to determine, is it going to get closer to positive infinity or negative infinity? So let's, this plus 2e squared, that's just a constant. It's spit in the ocean. It's not really going to, this is going to go to 0. But if I plug in like a huge, large, very large negative number here, but I square it, what's going to happen? Positive. Yeah, it's going to go to positive infinity. Now, if you're ever just like, really second guessing yourself, or you just want to do a quick check to see if you're right, just throw it in your graphing calculator and look at the graph and see, is it going up or down? And that way you'll know right away, okay, yeah, it's going up or down. I got that. All right, I think that's pretty much it.